Hi there, I'm Eric Steinhardt, and let's talk about what are sets. Let's start with some people. The name Diane refers to this person, Diane. And the name Betty refers to that person, Betty, with the checkered dress. But what about a phrase like the women? Diane is a woman and Betty is a woman, but what does the women refer to? The women refers to what? It refers to a dot. Well, what's a dot? That's not very helpful. Well, one thing we know about this dot is that both Betty and Diane are somehow involved in it, because Betty is one of the women and Diane is one of the women. So they are somehow both involved in that dot. Sets are dots. That's what sets are. They're not containers, they're dots. And you can see there's an arrow there from Betty to the dot and from Diane to the dot, and the dot is what the women refers to. The dot is a set that has these two women as its members. And so we can say that Betty is a member of that set and Diane is a member of that set. And I write it upside down so it goes in the right direction. Thinking of sets in terms of contests. Let's do that. Let's think of sets in terms of contests. So maybe there's some contest that Betty and Diane are in. One thing that can happen is they can both win in this particular contest. So Betty gets a trophy and Diane gets a trophy. They're both winners. We indicate that by Betty is a winner by writing winner, and then Diane is a winner by writing winner second. Another option is that Betty is a winner but Diane is a loser. That means Diane doesn't get a trophy. And so we've got winner-loser. A third option, of course, is that Betty's the loser and Diane is a winner. So we've got loser-winner. And the fourth option, of course, is they're both losers. Neither one of them wins the contest. And so neither one gets a trophy. So we've got four alternatives there: winner-winner, winner-loser, loser-winner, and loser-loser. Now let's think of sets in terms of selecting, that is winning, and rejecting, that is losing. Maybe Betty and Diane are applying to law school, and the law school could select them or reject them. It could select one or the other, or it could reject both. So there are four options. Let's suppose the law school selects both Betty and Diane. They're selected and selected. Thumbs up for both. Let's suppose that it selects Betty but rejects Diane. Too bad for Diane. So Betty gets the thumbs up, Diane is thumbs down. But maybe Betty gets rejected and Diane gets selected. Thumbs down for Betty, thumbs up for Diane. Maybe they both, unfortunately, get rejected from their desired law school, and so thumbs down for both. Thinking of thumbs up and thumbs down, or selecting and rejecting, is a little bit more active than thinking of winning and losing. So we can make selections and rejections, and of course rejection is just a negative kind of selection. Sets are ways of selecting. If we have a thumbs up, that's going to be a line to a dot. So thumbs up for Betty, thumbs up for Diane. There's a line from each one of them to a dot. Thumbs up for Betty, that means there's a line from Betty to a dot, but no line from Diane to the dot. Diane was rejected, and so Diane's not a member of that dot. Alternatively, if it's thumbs down for poor Betty and thumbs up for Diane, then Diane is a member of the dot, but Betty is not. There's no line from Betty to the dot, but there is a line from Diane to the dot. If it's thumbs down for both, we've got a dot, but neither one of them is connected to it. And there does exist a dot because both can be rejected, right? Sets are ways of selecting. Rejecting is just a negative way of selecting, and one way to select from Betty and Diane is to reject them both. So that dot exists. Here they are. Here are the two people, Betty and Diane, and the four sets that can be made from them. There's a set that just contains Betty, a set that has Betty and Diane attached to it, a set that has Diane attached to it, and the set that has nobody attached to it. So those are the ways of rejecting and selecting Betty and Diane. Again, with rejection just being a negative kind of selection. You can express this as a tree of selections. Select or reject Betty, and then if you've selected Betty, you can select or reject Diane. So if you reject Betty, then again you can select or reject Diane. So on the top branch, you select Betty and you select Diane. There they both are. They both got into their law school. And then you could select Betty. Maybe the law school selects Betty, but it rejects Diane. So Diane's not going. Or if Betty gets rejected, then Diane could be selected. And there you got Diane. But maybe, tragically, the law school rejects them both, and neither one of them are going. This tree of selections and rejections can be expressed as a binary selection tree, with 1 being selection and 0 being rejection. So, since there are 2 selection rejections, you get 2 digits to express each one. And there they are on the right. Ways of selecting exist. Ways of selecting things are objectively existing ways of doing things. Given some things, the ways of selecting them objectively exist. Ways of selecting things are sets of things, so sets objectively exist. We can do it with more people. Here's 4 people, Betty, Diane again, and Alan and Charlie. We can have sets of these people, thinking of them in terms of the women, the female people, the human, that's all of them, or the men, that's the male people. Or we can group them by their emotions. Betty, Diane, and Alan are happy. Poor Charlie, he's sad. So sets are binary selections. Given one thing, you can either select or reject it. So the number of sets of one thing is the number of binary strings of length 1. That's 2 sets, 0 and 1. Given 2 things, you can do 2 acts of selecting or rejecting, one after the other. So the number of sets you can make from 2 things is the number of binary strings of length 2. That's 4 sets, 0, 0, 0, 1, 1, 0, 1, 1. Given 3 things, you can do 3 acts of selecting or rejecting. So the number of sets over 3 things is the number of binary strings of length 3. That's going to make 8 sets. I won't list them. Given 4 things, there's 4 acts of selecting or rejecting, so the number of sets over 4 things is the number of binary strings of length 4, and that's going to be 16 sets. Let's break this down. Given n things, the number of ways of selecting or rejecting them is given by making binary choices n times in a row. Selecting over 4 things is 4 binary choices in a row. That's 2 times 2 times 2 times 2 such selections. And that's a total of 2 to the 4th power selections, which is just 16 selections. So there are 16 sets over 4 things. And you can see it illustrated in this tree. There is going to be 16 binary strings containing 4 digits, right? There are 2 possible strings of length 1, 4 possible strings of length 2, 8 possible strings of length 3, and 16 possible strings of length 4. It goes up by powers of 2. Given n things, there are 2 to the n ways of selecting them, so there are 2 to the n sets over n things. Each set can be represented by a series of 0s and 1s, with 0s as rejects and 1s as selects. So sets are ways of selecting. And given that there are n things, there are 2 n ways of selecting them. That's an objective fact about the world. There isn't some other number of ways of selecting. The world gives you exactly 2 to the nth power ways of selecting from among n things. So here's an argument for sets. Sets are ways of selecting, with rejection just being negative selecting. If ways of selecting don't exist, then you can't select things. Obviously you can select things. So ways of selecting exist. Therefore, sets exist. And that is an argument for sets. Thank you very much. I'm Eric Steinhardt, and this was an introduction to